So in the last video, we introduced autoregressive Gaussian processes, or AR processes for short, which were a type of Markov model that was appropriate for continuous valued data. And they have properties and setup which exactly mirrors the n-gram models that we looked at earlier for discrete data. And in this video chunk, I therefore want to look at one of the important properties of n-gram models in this new context, which is the stationary or invariant distribution for the process. And we want to talk about when it exists and how to compute it when it does exist. So in order to kick off our thinking on this issue, I want us to consider the example at the top of the slide, which is one we met last time, of an AR process, an Ar1 process, so a first order autoregressive process, where yt is generated by taking the previous value in the sequence and multiplying it by 0.9, and then adding a little bit of independent Gaussian noise to this value. So this is exactly the same way of describing the processes as below. And this is sort of what you would use to sample this on a computer. And I've produced a trace here of a typical value of y over time. And what I want us to think about is if we were to run this chain for infinity time steps, so all the way out here to t is equal to infinity, what would be the distribution at t is infinity that samples would be drawn from? And sort of conceptually, you can think about roughly what this means by setting off lots of samples from this process. So here's another one I'm sketching here rather badly, running this all the way out to t is infinity to give us a second sample of this thing. And I could sort of intuitively think about histogramming up those samples, and the question is, what is that density that histogram would be approximating? So I'm going to use this rather hokey notation to indicate that we're looking at the marginal distribution over the variable at t is equal to infinity. And really what this means is it means computing the marginal over yt as we limit t to infinity. The first thing I want you to think about to get us going here is what form, what functional form, what family will this distribution belong to? Not the precise details, but like what's the form of this distribution. So I want you to start by thinking about that, and then think, having hopefully solved that part of the problem, how we might proceed to calculate the stationary distribution. And you should take inspiration for their approach for solving for the n-gram models. So please pause the video, have a brief think about it. I don't expect you to get all the way there, and then we'll pick up this directly afterwards. Great, so hopefully you've had some time to think about it, and at the very least, I hope you managed to come up with this sort of chain of reasoning. Because everything is linear Gaussian, by that I mean if you look at the way all of our random variables, yt minus 1 and epsilon, affect other random variables, it's in linear weighted combinations. And we know that linear transformations of Gaussian random variables result in more Gaussian random variables. And so the marginal distribution in the limit must also be a Gaussian distribution, with a mean, which I'm going to call mu infinity, and a variance, which I'll call sigma squared infinity. And in order to compute the actual form of this stationary distribution, which will of course depend on the parameters like lambda and sigma squared, the parameters of our model, we can operate on the mean and the variance directly, rather than having to sort of manipulate the full distribution. We just need to compute what this thing is and this thing is, and then we're home and dry. So let's try and do that. And the property we're going to use to do that is that the invariant distribution, when passed through the transition dynamics, should yield the same distribution. So let's look at how the mean and the variance behave as we pass them through the transition dynamics above. So in particular, what I want us to do is look at how the mean at time t, which is the expected value under pyt of yt. That's the definition of a mean of a distribution. How this thing depends on the mean at yt of the previous time step, so mu t minus 1. And we know for the stationary distribution, those two things should be the same. Good. Okay, so this is not completely trivial to compute. There's a short way to compute this, and there's a long way to compute this, because we don't know what this marginal distribution is. Okay, so the way to go about this is as follows. There are ways which get you lost in mathematics, but I'm going to try and teach you the short solution. And the short solution is going to end up giving us a sort of a nice result that can be used all over the place. So this can be expanded. This is just the definition of what this expectation means. It means compute the average value of yt over the distribution, right? We're completely happy with that. And so I can actually rewrite this in terms of all the random variables which are present here. And the random variables, if I write up this equation that we had on the previous slide, look like this. So let's introduce those random variables here. We can introduce yt minus 1 and epsilon t, and we can integrate out these things. So we now have to integrate out not just yt, but also yt minus 1 and epsilon t. Okay. So I've introduced the full joint distribution over yt minus 1 and epsilon t, and I've integrated out yt and epsilon t. And so just to be absolutely clear here, the result I'm using is that pyt, the marginal distribution over yt, is equal to the integral over the joint distribution of yt minus 1 of epsilon t when I have marginalized out the yt minus 1 and the epsilon t. Okay, this is nothing other than the sum rule. Now for continuous variables. Okay, good. And the reason why I've done that should be apparent on this next line here. So I'm going to use the product rule now to decompose that joint probability. And I'm going to decompose it into the probability of yt given yt minus 1 and epsilon t, the probability of yt minus 1, and the probability of epsilon t. And I've got my integrals now to put back in again. So notice here, of course, that epsilon t is independent from yt minus 1. That's why we can write this as a product. You can see that up here. You can see that epsilon t only affects yt. It does not affect yt minus 1. Epsilon t is something you add to lambda times yt minus 1 to generate yt. It's not going to change the value of yt minus 1 if you change the value of epsilon t. So they are independent random variables. Good. Okay. And now we're starting to make some progress, because this thing, this transition is given by this equation up here, i.e. yt is deterministic given yt minus 1 and epsilon t. So this thing I can actually write as a delta function. So let me make that explicit. So we can write this as integral yt delta yt minus lambda lots of yt minus 1 plus sigma epsilon t. Then we get yt minus 1 and epsilon here, and then the integrals. Good. And this has almost got to the result that I wanted to get to, kind of running out of space here, so I'm just going to zoom in. So I'm now going to do the integral over yt. Okay. And what that's going to do is it's going to pick up this delta function contribution, and it's going to set yt equal to this bit of the delta function. It says that yt has to take the value lambda times yt minus 1 plus sigma times epsilon t. So that means then that our integral becomes integral y t, let me just put the lambda in, sorry, integral of lambda yt minus 1 plus sigma epsilon t times p yt minus 1 p epsilon t dyt minus 1 d epsilon t. I've done this integral, so this one disappears. And now we can see we've got a really simple form. If I was to summarize this, this looks like the expectation under yt minus 1 and epsilon t so I'm running out of space here. Let me just move this up slightly so I'm not battling the desire for this thing to change the page. So this thing is equal to expected value under yt epsilon t of the thing out the front here, this term out the front, which is just lambda yt minus 1 plus sigma epsilon t. Okay, so what have we done here? And why is this important? So we said we want to compute mu t, which is just the mean of the variable at yt over the marginal p of yt. And that's the thing we're going to take the limit on in a minute. And by applying the sum and the product rules and the structure of the model, we end up in this form here, where we just have to take the expectation over, sorry, there's a slight typo here, expectation over the previous marginal distribution, that was the important thing here, and the noise of this thing in here, okay? So this, we're starting to write it down into a recurrence relationship, essentially, where we look at on the left-hand side here, we've got the expected value of yt, and on the right-hand side, we're going to get stuff which is involving the expected value of yt minus 1. And this rule is called, sometimes called the rule of conditional expectations. So we're now going to use this rule to complete the proof. Let me just erase all of our derivations here, and I'll just summarize the rule at the top here. And then we'll use it to complete the derivation. So this thing is equal to the expected value over p yt minus 1 p epsilon t of lambda yt minus 1 plus sigma epsilon t. I think, to be honest, this rule is kind of obvious. Essentially, we've substituted in here for what yt is, and we've made sure we take expectations to all of the source of randomness in this new form for yt. So some of you, I think, probably could have leapt to this directly, but other people ask questions about where it comes from, so I've gone through it rather laboriously. Great, okay, and now we can proceed to carry out these expectations. So you'll notice that this first term here does not depend on epsilon t, and so when we take the expectation inside, this first term is just going to give us lambda lots. I can delete this thing down here now as well. Lambda lots of the expected value of yt minus 1, which I'll call mu t minus 1 in analogous definition to this thing. And then the second term here doesn't depend on yt minus 1, so I can forget about that. And I can just average it over p of epsilon t. And of course, the average value of the noise is 0, as shown up here. So this thing, when I compute expectations of it, the expected value under p of epsilon t is equal to 0. Great, so this all comes down to the following equation, that the mean of the marginal distribution at time t is equal to lambda times the mean of the marginal distribution at time t minus 1. And so if we then take the limit that t tends to infinity, this implies that mu infinity is equal to lambda times mu infinity, essentially. And the only way that can hold, the only way for these two means to be the same, because in the limit, we're going to assume we're in the stationary distribution, in which case mu t minus 1 will equal mu t. The only way that can hold is if mu infinity is equal to 0. Okay, so this shows that the mean here is equal to 0. Let's do the same thing now for the variance, or more properly for the second order statistics of yt. Okay, and you can use exactly the same trick that we did above, and I won't go into as much detail deriving it now. We'll just use the trick directly. Okay, so we're going to compute what's the expected value under pyt of yt squared. And this thing is going to be equal to the expected value using the trick we just talked about, the expected value under yt and the distribution of the noise of, well, what's yt squared? It's lambda times yt minus 1 plus sigma epsilon t squared. Okay, so it's using the same expression as before, essentially, but now the thing inside the expectation is a little bit different. Good. So let's just multiply out that quadratic form and talk about the terms. So this is equal to expected value under pyt of p and p epsilon t of lambda squared yt minus 1 squared plus, let's do the cross term next, 2 lots of lambda sigma yt minus 1 epsilon t plus sigma squared epsilon t squared. Good, so it's just multiplied out that quadratic form, and now I can take the expectations inside the bracket. So notice this first term doesn't depend on epsilon, so I can just write this as lambda squared times expected value of yt minus 1 squared. Notice this is the same as the term on the left-hand side, the same sort of quantity here. So this is the thing where our recurrence relationship is going to be generated from. This term, second term, gives us something like plus 2 lots lambda sigma expected value of yt minus 1 under p yt minus 1 and expected value of epsilon t. This again evaluates to 0, so that cross term goes. And this is coming from the fact that these two variables are independent and the mean of this variable is 0. So this cross term disappears. And then finally we get this third term here, which is plus sigma squared epsilon t. Sorry, let me just explicitly put in the expectation here. And this thing, the expected value of epsilon squared, we can go up to our distribution and see, oh, that's equal to 1. Because the mean is 0 and the variance of this distribution is 1. And so the mean plus the variance is equal to 1, which is the average value of epsilon squared. So I can set this thing here equal to 1. Okay, so let's put this all together and collect everything up. So we know that the expected value of yt squared is equal to lambda squared times the expected value of yt minus 1 squared plus sigma squared. Okay, so this is the recurrence relationship for the value of yt squared under the marginal. And now what we do is take the limit again. We take the limit t is equal to infinity. And in that case, we'd like this square value to coincide with this square value. And also, because the mean is tending to 0, in the limit, the mean is equal to 0, this thing is equivalent to the variance of the stationary distribution. And that must be consistent across time steps. So we can write this plus sigma squared. And then if I rearrange that formula, I'm going to get, and solve for sigma infinity squared, I get that sigma infinity squared is equal to sigma squared over 1 minus lambda squared, just solving for this thing. So sigma squared over 1 minus lambda squared, that's what this guy is equal to. Okay, so this is a fairly long-winded calculation. I've actually made it a bit more long-winded in the effort to make everything completely explicit here for you and all the steps sort of carefully spelt out. You can leap straight to this result, I think, in most cases without thinking too deeply, but I've gone through exactly the proof of it. So I just want to sanity check the answer before we wrap this up. And there's a couple of different things which hopefully strike you about this solution. Firstly, if you make the process noise here, this sigma thing bigger and bigger, so there's more noise injected between each state, intuitively that should make the marginal distribution broader. It will just scale the fluctuations here by a constant factor. And so that does indeed show up in the right place. You can see here that if we make sigma bigger, we make the marginal distribution proportionately bigger. The thing that's perhaps less obvious is this denominator term, the 1 minus lambda squared thing on the bottom here. And in particular, as lambda tends to 1, bad stuff happens. The variance blows up, and it can tend to -1 or +1. You'll get the same effect. So what's going on there? Why is the marginal variance blowing up as lambda tends to 1? So let's go back and consider our sort of master equation at the top here. What happens in this master equation as this thing tends to 1. So let's replace this thing with lambda equals to 1 here. So I can just remove that term from the equation because we get 1 times this thing out front. And then notice now that yt is equal to yt minus 1 plus some noise. And I could actually substitute this formula back into here in for yt minus 1 to get us an expression for yt in terms of yt minus 2. So we'd get yt is equal to yt minus 2 plus the noise we introduced at that time step plus the noise we had from the current time step. We get this expression. You can see what's happening here. If I carry on unrolling that, is we're just adding up noise, Gaussian noise, scaled by this factor sigma. And as I continue to unroll this thing backwards, you can see that we're just accumulating more and more random noise as we move through the process, as we move through time here. Because there's no shrinkage term here, no lambda that's pulling us back towards 0, we're just adding up more and more noise, and in the limit we'll get something of infinite variance. And that's why as lambda tends to 1 here, we're ending up with a marginal variance that tends to blow up. It's essentially a perfect integrator. Good. So this is sort of roughly speaking why the different parts of that solution make sense. So the thing to take away from this is there is a concept of a stationary distribution for these AR Gaussian models. We can compute them using recurrence relationships. If lambda is too big, then these processes will diverge and there won't be stationary distributions. So if lambda is bigger than 1, for instance, this will diverge. So hopefully you can see how similar concepts from the n-gram models carry over in this case, and it's also a good workout for your Gaussian algebra to brush up and make sure you know these tricks for calculating these things efficiently, and I hope I've walked you through that in a clear way.